I'm R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this video, we will discuss the topic Maxwell's equation in integral and differential form for the course Electromagnetic Fields and Waves. So the Maxwell's equations are given foundation to the existence of electromagnetic waves. The valuable work done by James Clerk Maxwell helped in discovering electromagnetic waves. And the time varying fields are involved in the experiments of Faraday, Hertz, and the theoretical analysis was done by Maxwell. And Maxwell's equations are nothing but a set of four expressions derived from Ampere's circuital law, Faraday's law, Gauss' law of electric field and Gauss' law of magnetic field. And these four equations can be written in the following forms. The first form is point form or otherwise called as differential form, and the second form is known as integral form. So the Maxwell's equation, first equation is which is derived from Ampere's law. We know the Ampere's law relates the line integral of H around the closed path is equal to current I enclosed in the circuit, that is integral over the closed surface H dot dl equal to I. But we know that I is the current, which is the integration of current density over the surface. So in equation 1, I is replaced by integration of J ds. And this equation will be true when we add the displacement current density to the conduction current density. So we can modify equation 2 as integral of H dot dl is equal to integral over the surface J plus dou d by dou t dot ds. And this relation is called Maxwell's first equation derived from Ampere's law. And now applying Stokes' theorem in order to get the point form, according to Stokes' theorem, integral over the surface del cross H dot ds equal to integral over the surface J plus dou d by dou t dot ds. By removing the surface integral, we get del cross H equal to J plus dou d by dou t, which is the differential form of Maxwell's equation derived from Ampere's law. And next we are going to see the Maxwell's equation derived from Faraday's law. According to Faraday's law, the induced EMF in a circuit to the time rate of decrease of the total magnetic flux linking the circuit was given as V is equal to d tau by dt. And here the flux linkage by the surface integral B over the area bounded by the circuit is given by the relation V is equal to minus dou by dou t of integral over the surface B dot ds. So by equating both the magnetic flux equation, we get E dot dl is equal to integral over the surface minus dou b by dou t dot ds. Now the first relation is generalization of Faraday's circuit law, and the previous equation, equation 7, is called Maxwell's equation derived from Faraday's law. And now in order to get the point form, we apply Stokes' theorem, and after removing the integral, we get del cross E is equal to minus dou b by dou t, which is the point form of Maxwell's equation derived from Faraday's law. And now we are going to see the Maxwell's equation derived from Gauss' law. Gauss' law relates the surface integral of the electric flux density d to the charge q was given by integral over the surface d dot ds equal to q. By replacing q by the volume integral of the charge density rho throughout the volume enclosed by the surface S, we can write in more general form as integral over the surface d dot ds equal to integral of rho dv. So now by removing the equation, we get del dot d is equal to rho, which is the Maxwell's equation derived from Gauss' law. And finally we get the magnetic fields of the surface integral B over a closed surface yields 0. Thus the magnetic counterpart of Gauss electric relation is integral over the surface B dot ds equal to 0, and the corresponding point relation is del dot B is equal to 0. And the equation 12 and 13 are Maxwell's equations derived from Gauss' law of magnetic field and in point form and also integral form. And now the Maxwell's equations are given either fundamental relations, and they are very important in dealing electromagnetic problems. So along with this Maxwell's equation, important equations we must know in electrostatic fields are J is equal to sigma E, del dot J is equal to minus dou rho by dou T, F is equal to QE, dF is equal to I cross B into dl. And Maxwell's equation in free space, it is a dielectric, so no conductivity term, so conduction current density is 0. So in the first term, integral over h dot dl dou d by dou t, conduction current density is put to 0. And the second equation, E dot dl is minus dou v by dou t dot ds, there is no change in the equation. Third equation, d dot ds equal to rho v is 0 here, so d dot ds equal to 0, b dot ds also 0. So free space differential form, del cross h is dou d by dou t, del cross e is minus dou v by dou t, del dot t is 0, del dot b also 0. For harmonically varying fields, d can be substituted as d naught e power j omega t. D naught is the amplitude and e power j omega t is the phase term. So dou d by dou t gives j omega d. So by replacing we get harmonically varying fields, del cross h as sigma plus j omega e in epsilon into e, del cross e is equal to minus j omega mu h, del dot t is equal to rho, del dot b is equal to 0. So all these different categories of the fields, all the Maxwell's 4 equations are given in the table. So now the assessment. Differential form of Gauss law in magnetostatic is Gauss law of it is divergence of B is mu j. And in vacuum or free space, what observations are made? And in vacuum or free space, and conductivity is equal to 0. So thank you.